Okay. This question appeared in 2023 December examination. This question is from classical thermodynamics topic. The thermodynamic variable x in the equation dou S by dou P at constant temperature equal to 1 by T x plus dou H by dou P at constant temperature is. So we need to find out what should be that thermodynamic variable x supposed to come here. Okay. So we need to find out the thermodynamic variable that should appear here, right, in this equation. So here this equation, just go through this equation carefully. It has entropy term and enthalpy term. Okay. So we know very well the standard thermodynamic equation which connect enthalpy and entropy. dH is equal to TdS plus VdP. Okay, this equation is a standard thermodynamic equation. You all well known about this. Now what I am going to do, differentiate. Okay, so we need to keep temperature constant here. See, just note down, temperature should be constant. So if we keep temperature constant, and we need to differentiate with respect to pressure. So what I am going to do, I will differentiate this with respect to pressure, keeping temperature constant. Similarly, keep this T as such, differentiate S with respect to pressure, keep temperature constant, plus keep this V as such. If you differentiate dP with dP, you will get 1. Okay. So dou H by dou P at constant temperature equal to T into dou S by dou P at constant temperature plus volume. Okay. Now we need to keep dou S by dou P in the left hand side. So what I am going to do, I will bring this plus volume term to the left hand side. So we get dou H by dou P at constant temperature minus volume equal to T into dou S by dou P at constant temperature. We need to keep this term in the left hand side. So I'll divide throughout by T. Therefore we get, so let me write this one in the left hand side, dou S by dou P at constant temperature. I am dividing throughout by T. So this T cancels. So in the right, we will have dou S by dou P at constant temperature in the right hand side. I'll write that in the left hand side now, equal to, divide throughout by a temperature in the left hand side also. So instead of that, I will just put 1 by T into dou H by dou P at constant temperature minus volume. Okay. Now just compare this and this. Here we have dou S by dou P at constant temperature. Here we have 1 by T, and plus dou H by dou P at constant temperature is available. Then in the place of X, we have minus volume. So X should be minus volume in this case. Okay. Therefore the correct option for this question is option C. Right. So it's a very simple question. Try to remember the standard thermodynamic equation. You know very well there are 4 standard thermodynamic equation. One in terms of internal energy, second one in terms of enthalpy, third one in terms of Helmholtz free energy, and fourth one Gibbs free energy. Okay. Right. Now let me move on to the next question, which appeared in 2023 December. Here I am going to discuss classical thermodynamic questions. Okay, specifically. Right. Let me move on to the next question. Yeah. This is the second question, appeared in 2023 December. Just go through this. A PV diagram is given. See, in the y-axis pressure is given, and in the x-axis volume is given. So PV diagram. Right. Here the system moves from A to B, then B to C, then C to A. Listen, since it is a cyclic process, right? It starts from A, then it completes the cycle and comes to the initial state A again. Okay. So it is a cyclic process. Now we'll go through the question. The total work done by the system in the cyclic process depicted above is. So what is the total work done in this? So we need to identify that. Yeah. So we need to find out what is the total work done in this process. Okay, remember in PV diagram, if a cyclic process is given, if a cyclic process, something occur in a cyclic manner, and if the cycle goes in the anti-clockwise direction, then work done should be positive. Work done by the system is positive. In the PV diagram, if a cyclic process occurs and if it occurs in the clockwise direction, then work done in this case should be negative. Right? Instead of PV diagram, suppose sometimes they'll give VP diagram. If VP diagram is given, okay, and if the process is cyclic and if it occurs in an anti-clockwise direction, in this case work done is negative. If in VP diagram is given and the process is cyclic process and it occurs in clockwise, in this case work done is positive. Just remember this information, it's very, very important. Now it is a cyclic process. It starts from A and goes to B, then B to C, then finally it comes to the same state A. Okay, so it is a cyclic process. And this cyclic process occurs in the anti-clockwise direction, right? See this? It occurs in the anti-clockwise direction, right? So, and it is PV diagram, right? PV diagram. In PV diagram, we have a cyclic process which occurs in the anti-clockwise direction. Therefore, the work done should be positive here. Work done should be positive, right? Total work done. I'm talking about total work done. It should be positive. Now listen, to find total work done, right? See the shape of the cyclic process. Now it is a right angle triangle. Okay, the area under this triangle will give you the total work done. In PV diagram, if cyclic process occurs, then the area covered by the circle or the cycle will give you the work done. So in this case, the cyclic process occur in a right angle triangle manner. Therefore, the total work done is nothing but equal to area. So it is nothing but area of triangle ABC, and in this case area. In this case, the triangle is a right angle triangle. Okay, therefore what I'm going to do, for right angle triangle the formula is half into base into height, right? Base into height. So B into H. You know very well, half into B into H. Half into, what's the base here? What's the base here? See, this volume is 3V1 and this volume is 1V1. Therefore, this difference is 2V1. So 2V1 is the base. And what about the height? 7P1 is the pressure at this point, and pressure at B is P1. Therefore, the difference is 6P1. So 6P1 is the height of the triangle. Okay, so base of the triangle is 2 into V1 and height of the triangle is 6 into P1, right? So if I simplify this, 2 cancel each other, I'll get 6 into P1 V1. This is the total work done by the system in this cyclic process. Okay, so the correct option for this question is option A, right? Take note. Now let me move on to the next question. See, this question appeared in 2023 December. Okay, now one more question appeared from classical thermodynamics topic in the same examination 2023 December. This question is somewhat interesting. See, the application of Euler's reciprocity relation to the volume of 1 mole of an ideal gas results in a mixed second derivative of volume, which is equal to, okay, listen, Euler's reciprocity you know very well, right? If the function is a state function, then you can write the Euler's reciprocity, right? So here 1 mole of ideal gas is given, right? So for 1 mole of ideal gas, for 1 mole of an ideal gas, we can write the ideal gas equation as P into, since there is 1 mole, volume should be molar volume equal to number of moles is 1 into RT. Okay. Yeah, PVM equal to RT, or molar volume equal to RT over P. Now see here, we have two variables here. R is constant. We have two variables, temperature and pressure. Now you should take the second derivative. See, you should take the second derivative of volume. One, see, Euler's reciprocity relation, right? It is actually a cross relation, cross derivative actually. Cross derivative in the case, first differentiate V with respect to pressure or temperature, then differentiate with the next variable. Okay, so what I'm going to do, first I'm going to differentiate V with respect to temperature. Okay, keeping pressure constant. We keep pressure constant, so what we get is R by P. I'm differentiating with respect to temperature. Now we should find out, say, according to Euler's reciprocity, you have to differentiate, cross differentiate this with the two variables. I have differentiated with the temperature. Now I'm going to differentiate with the pressure. So dou square will get second derivative, dou square Vm by dou P to dou T. I am differentiating this with respect to pressure now. So pressure is, see here, pressure is exists as 1 by P. If you differentiate 1 by x, you will get minus 1 by x square. So 1 by P, you will get 1 by P square. So you will get minus R by P square. This is the mixed second derivative of volume for 1 mole of an ideal gas as per Euler's reciprocity. Okay, so the correct option for this question is option A. Right? Yeah. So these three questions were appeared in 2023 December from classical thermodynamics topic. Okay, in the next lecture we'll discuss classical thermodynamics questions from the earlier examination, that is 2023 June. Okay, yeah, I stop here. We'll meet with the next lecture. Okay, thank you for listening.